technical. Sorry, like a little bit technical for some audience, but please feel free to ask me questions if there's some confusions. So let me, before the talk, good, I think I'll try to do this way. So before the talk, I would like to thank all my group members and my collaborator who contributed to the research. So a lot of my group members already graduated and they are becoming assistant professor in other universities or joining other group as postdoc. With that, I really want to thank all of them. Unfortunately, they are not here because of COVID. So, but let me give a quick motivation for the work. So as we're already seeing in the past decades, there's an explosion of data, especially in the image data and the language data. So with the explosion of the data, we're seeing a revolution in the learning, like taking the image photos as an example, with more and more image data. So the deep learning outperformed humans in the object detection. And this generated a lot of excitement, right? Now we see deep learning almost in every area. So besides the image and language data, there is another explosion of data, another type of data, IoT, Internet of Things data. So like our society has more and more smart and connected devices, which are capable of sensing, communication, computation, and actuating. So with this kind of data and with our advances in learning, people are starting visualizing smart systems. For example, smart home, smart transportation, smart manufacturing, smart grids, and in general, smart cities. But this is like one question I would like to pose, right? Does more IoT devices, like smart devices, really means we can really making our system smarter by using the existing deep learning technologies? So when we try to look at the examples, so indeed, on the one hand, we have seen many exciting news. Like this is a video from Boston Dynamics. I guess almost every year, Boston Dynamics will generate exciting video to see how Atlas is capable to do tests. I don't think I will ever able to read those texts. But if you also do another Google, you will also find similar videos that Atlas fails by doing the similar tasks. So the laugh actually, like we can laugh at these videos. The next news is actually a bit more cruel or like tragedy. So speaking of the societal system that I was motivating the work, right, which is closer to our daily life. So this is the power grid. Earlier last year, so everyone remember the news. So in Texas, there's an unexpected big winter storm. To address the winter storm, the ERCOT has to do the rolling blackout. So millions of people's life got affected. This is what we did for power system once we see some urgency. And speaking of the transportation, on the one hand, so we see lots of tragedy news about car crashes for autonomous driving. But on the other hand, let's say even if we solve those safety issue in autonomous driving, how to put in the technology together to really reduce the traffic jam and to improve our mobility is even a bigger question. I put in those like news together, just want to motivate the one question, right? The learning for societal, physical, dynamical system is hard. How can we do it? Let me take a step back. So my background is from controls. I want to like look at the system from control perspective. So what's really going on with our societal system? So we have a societal system and we are building a lot of different IoT devices that is capable to monitor the local situations and passing the real-time data to the edge devices or to the data centers. So once the data being arrived at the edge devices or data center, the data is being shared with the devices and being processed by the advanced algorithms. The decisions can be made and passed through the actuators, which can take the real physical actions. So we look at this feedback diagram, it's fitting to our standard feedback control diagram nicely from our textbook. But what's the difference here? So the difference is this. First of all, we have imagine the big smart city. We have a really big system and we have the actuator devices that's being located at different locations. So there's a huge number of devices and they're generating a huge amount of data in real time. So even though we have advanced computation communication the technologies, but if you track into those existing communication information technologies, every technologies come with its own limitations. So it's very hard to deal with the scale of the data we're really dealing with. That's the first challenges. Another thing, imagine like on the one hand, people getting excited, everything is connected. But once we connect all the devices, so the active point, they active at the same time. If we don't recording them well, they should generating a lot of random fluctuation to each other. So the system having more and more uncertainties, this is harder to analyze. It's making the system is harder to model. Like every time we go to model, just model small component, it's not enough. So it's hard to model, hard to control. Besides, like we're talking about physical systems, there's always those robustness, safety, stability issues that we need to worry about. So those are the opportunities and the challenges. So definitely like because those challenges and because the advances in learning, so recently there's a great interest in developing the data-based learning method for those physical systems. And taking the reinforcement learning as an example, so we have been seeing many exciting news from DeepMind, like the AlphaGo, the DeepMind doing the video games, and right now like doing the robotics in the control environment. So those news are very exciting in the sense of like, this looks very cool. We even don't need to model the online dynamical system. Like if you think about how people play Go, it's very hard to model what the other player is really thinking, what he will want to go to, what he really want to take the action. But it's okay, right? So for those applications, I don't need to really model the online model. I just keep playing and observing my stay, reward, I refine my action, and eventually I can outperform the best player in the world. And because of exciting news, it's no wonder more and more people starting to adopt the learning method to handle dynamical system. So dynamical system typically with the goal, right? I would like to design the controller, taking the input, generating the control action to shape the dynamics of the system to achieve certain objectives. So how are we going to use the reinforcement learning method? We apply some control strategy, and we can run simulation, or we can put in the control strategy into the physical system directly. We're observing the outcome. Once we have more and more observed data, we can go back to refine my control strategy and keep doing this loop. There are many different types of methods being developed in the control and reinforcement learning community. And typically the method people classify into two categories. So one category people call as model-free method. In the model-free method, as what I mentioned before, that people do not need to remodel the dynamical system. Just apply the strategy, observing the outcome, figure out a way to improve it. And many methods develop according to this kind of philosophy, like policy gradient, critique, some Q-learning, which I will talk about a little bit more in the later of the talk. And there's another type of model-based method, especially once we really want to worry about the safety of the system. So I have some physical knowledge of the system. I go ahead to connect the data. I will try to estimate the model first. Once I have the model, I can go back to using my control design approaches. So both methods work well for some simple systems, but what are the challenges? So first of all is, even we look at the exciting news from DeepMind, and we dive into how much computation they really solve, they really need to use. It's a huge amount of computation. And imagine the IoT devices in the physical system I was mentioning before. It's hard to imagine how we really have this much computation resource for individual small devices. And how can we really scale this algorithm to the large scale system? That's the first challenge we need to handle. And secondly, about the high performance guarantee. So many exciting news, they did a lot of empirical study, eventually some policy come up and becoming the best policy. But when we really put in those policies, like think about physical system into the real uncontrolled environment, we need better performance guarantee. I call that the high performance guarantee, like depending on application, right? We really worry about safety, it's going to crush the system. And for the aircraft we talked about before, like stability is a very important issue. Right? We cannot just say probability, like with probability 75%, I guarantee it's stable. This is really low probability guarantee. And how can we really guarantee those physical challenges like safety, stability, robustness? Like for the following the talk will become more technical. I don't have answer to say, oh, we have a like amazing algorithm that Boeing company can go direct to take. It's just we are heading to that direction. First, we think like my group is doing theoretical work, right? First of all, theoretically, what exactly we can say? Like what are the one, like how can we really even combine those model-free, model-based methods, taking advantage of both methods to achieve something that's not really achieved before. So just I want for this talk, I want to put in 2 examples to show how we can really use in those learning ideas, plus the control we already developed together to address the scalability and to address the safety to a certain degree. So as another example, I also like the first part of work, I will talk about scalable reinforcement learning for network systems. And the first, as you will see, the algorithm is more aligned with the model free, but not exactly model free. The second part is more model-based because the second part talk, I really want to guarantee part safety guarantee. So far we haven't really figured out a way to do the total model free for safety, like it's better to do the model-based method. Any question for the motivation? With that, I will dive into the details. So first, as I mentioned, first I want to talk about how we can develop IO methods that scale up to the large scale system. So I put in the examples here. And I put in a black box. As I mentioned, if I just grab some reinforcement learning method, then we're just treating the online physical system as a black box. But the way I'm going to show you is this. Like if we just treat the black box, as you can see before, it's really hard to scale up. The key for our algorithm design is to using some network structures that we probably already know. Like it's sometimes certain knowledge about connectivity of the network that is able to obtain. So how can we use this network structure to develop the scalable method? Now become a little bit technical to solve the problem. So please follow with me. So this is the physical system. And we have a different, you can think about each node as an agent. And we have time t. Each time I need to make a decision at each time t. So I will create stage or time. At each stage, for each agent, I have one state variable to describing what's going on with this agent. I have one example later on to show it, like where this comes from. And for each agent, let's can imagine for the devices, they can take actions. So that action they're going to take. So once they take action, so for this study, I'm focusing on the finite case, finite state space, finite action space for each agent and for each action. So what we can do. So where does the network come from? So network comes from the state transition. So the difficulty for dynamical system is always like my current action will affect even my long-term trajectory. So the S state here is kind of the trajectory. So the state transition develops the network. What it says is at each time, for one agent, my next state will depend on my neighboring state and my own action. This state transition will determine who is connected to who. If my state will affect my neighboring state, then there's a link between this agent. Clear for this setup? So what we're going to assume is we do not really know the exact state transition. And you can imagine for the traffic network, we roughly know that the traffic jam will affect the traffic jam for the next road. But what exactly the rule is very hard to get in the exact model. So this is unknown, but the relative structure, the net structure, we have the information. For transportation, we know the network. For the power grid, we know the network. So what's the reward? So for this case, we assume we have state reward for every agent. Like if you imagine for the traffic jams at each road, like how bad the traffic jam at each road section. That's called as a reward or the cost function. The goal is to developing some control policy that's based on how well is the entire system. I would like to take the action in order to maximize the long-term reward. So the control policy is just a mapping from the state space to the action space, and the objective is just sum up all those long-term state rewards. I have a discounting factor. You can also change the reward function to be other reward function. Now, let me repeat that. The local React interaction defined by the state transition, and that is the key for us to develop the algorithm. Let me give some examples. So first is the epidemic, like the COVID. You can imagine here, the probability of one agent getting infected will depend on whether the neighbors get infected. Right? How exactly is the probability? That's hard to model, but roughly you know who are the person you generally interact with. And for the traffic, as I mentioned before, what we can imagine is about congestion of one road will depend on the nearby roads. That's where the local state transition will come from. Now, let's look at how hard for this problem is. So first of all, we try to think about for the reinforcement learning algorithm, if I just grab any kind of IO algorithm developed by the community already. So the first challenge we're going to have is a state action space will grow exponentially fast. What do I mean by that? So even for individual agent, say only has a two choice, just go left or right. But once you think about the entire system, we have 2 to the power of n choices for individual agent, for all the agents together. I need to figure out the best, which is very challenging given the space of dimension. And so that's why like the standard reinforcement learning algorithm will immediately fail to handle this problem. And of course, people actually know these challenges for a long time. And there is a very nice fundamental theoretical paper to say how hard the problem is. And that's why people recently developing more approximation method to approximate solution. But one challenge I mentioned, like for the hard performance guarantee, there's another level of hard performance guarantee is how good exactly this method. I know I'm going to sacrifice optimality, but how sacrifice I am. That's the first challenge. Now let's look at the second challenge. Like think about transportation system in your mind. Right? Let's suppose there's a magic learner actually learn the policy and which can tell what's the action I should take based on the global system. And now think about the challenge, how are we really going to get this global information? Even if you drive using your Google map, it's just one local neighborhood. So what this means is for the policies wise, even we have a global policy is available, it's impossible to re-implement in the real physical system. So that's motivate us to look at the local policies. So for the talk, I will just focus on the extreme case. I want to see the algorithm, like for individual agent, I just want to take action based on what I observe locally. And you can relax this one to including some information from your neighbors, adding communication, but we just look at the exact local communication. Even with this, it looks like now I'm only dealing with a local policy, just based on my own local state. For this paragraph, I want to show is I still need some communication. So imagine I will take in some local policy based on my own local reward, my own local observation. But since online physical system is still connected, so what I really take during the transportation will affect the long run. So even during the learning policy, the learning phase, if I want to find a good local policy, what we need is we still need local communication with neighboring, or you can build in some other communication graph in order to find the global local policies. So the question, in summary, what I want to say is like, the question is how can we using the local state reward communication in order to learn a good local policy? I put in a quote on the first local here because I haven't really defined it yet. So what is that local communication do we really mean? What if I have like more powerful communication? I can look at my neighbors for a few steps ahead. Let's look at how the algorithm really we can design. So for the audience who are not familiar with IO, this is a very quick review of the IO method. So how people like for the policy gradient method. So how people design this IO method, this is one example. So I'm going to, eventually I just want to find a control policy. So I can parameterize my control policy by a certain parameter. Here is the theta as a parameter. So once I parameterize my policy using the theta, I can write down my long-term objective function in terms of function of theta. Now I can take in the policy gradient. So we have optimization expert here, right? If I recognize the optimization problem, I can just take in the gradient step. But here's the difficulty, as since I do not know the state transition rule, it's impossible for me to really have the gradient of the function. How people do it? The way people handle it is to using this nice policy gradient theorem. So don't be scared by this mathematical notation. The important message is this: the policy gradient theorem connect with my state reward observation with my policy gradient evaluation. And the key is the Q function here. So what the Q function is, it's called the Q function, but the meaning is very simple. It's expected long-term reward. I need to evaluate if I take a policy. So how exactly my long-term reward is going to be? Starting with the state, starting with the action A. So that's called the Q function, like just long-term expected reward, which makes sense, right? If I want to really improve in my policy, I need to kind of estimate how well I'm going to do in the long run. And with this kind of policy gradient theorem, there's so many different types of reinforcement learning algorithm. This is the one framework, the active predicate. At each policy gradient step, when I update my policy, I have that's called the actor step, do the policy gradient. And for the critic is I just go ahead to estimate my long-term reward better and better. So you can see one of the key here is to evaluate the expected long-term reward. And people sometimes call it a Q table because you think about SA, the stress element, you have a big Q table there. The challenges, as I mentioned before, the space of the state and action for our multi-agent system grow exponentially quickly. So the Q function is extremely large. And moreover, when you evaluate, I need everyone's information, which is impossible to implement. So how are we going to do it? Let's really write it down, right? I want to study my localized policy. And for every agent, just have one parameter, theta I. And based on my information, SI, I want to take action. And this is the global policy parameter. It just augmented everyone's action, everyone's policy. So I just force myself to go ahead to implement the algorithm. So first of all, I ran a Q function. I just put in summation of everyone's reward together and do some exchange of the summation. I can have something which is very intuitive defined called the QI theta here. What it says? It says the Q function for the global system is a summation of individual QI, which is a long-term reward for individual agent I. If I'm the agent there, I just need to figure out a way to evaluate how good my long-term reward. But even I call it a QI, but it will still depend on the global system, global state, global action. I haven't really achieved anything yet. Still exponential in large tables. And the policy gradient, I need summation of everyone's Q function. Which I haven't really achieved anything. So I put in the question here. But at least I have some intuition right now is if I really want to do some learning, I need to figure out a way to evaluate my long-term reward. Now imagine you are the agent I in the network. What are you going to do? It's impossible if I really want to evaluate based on the entire system state action, how good I am. I don't have other people's information. So one naive solution is usually actually I will do it. Is I truncate. I don't care who are the people outside of my region. I pick some neighbors. I look at for my friend what they're doing and evaluate how I'm doing, how well I am doing. Right? This is just a truncation, kind of which is a lazy method. But what I want to show is the truncation, this kind of intuition that how we make a decision making, it's actually worked for this case. And what do I mean by the work and how? The reason why for this network control problem, why it's work, because it has nice property, exponential decaying property. So what exponential decaying property says? It says for the two agents, if one agent is really far away from another agent, then the state and action that he's going to take just has a very negligible effect on the other agent. And the further the two agents are far away, the effect will decrease. And the decaying rate is actually exponential. So you might ask why this holds. So we have a technical thing in the paper to explain where this exponential decaying property come from. And we actually can show no matter what kind of network system that we talk about, as long as it satisfies the model I set up before, it satisfies this exponential decaying property. With this property, now you can look at here, my truncation method actually going to work. So when I develop my learning method, I don't really need to worry about the entire system. And depending on my computation and my memory ability, I can pick how many neighbors I want to look at. If I pick more neighbors, then I will lose less optimality. If I only pick one, or even I just look at myself, or I can still achieve certain kind of optimality guarantee depending on the decaying factor. So this is the first, we kind of handle one challenge is the Q function. We can just make the Q function based on the local agent. And then another challenge is the policy gradient variation. I need everyone's Q function. Very interestingly, we can also ignore the people who is far away from me. Just using those local Q function from my neighbors, we are able to achieve our goal. And because exponential decaying property, we're able to show the estimated gradient is a good approximation of the true gradient. With these two elements, you can imagine what we're going to develop the algorithm. We're just going to have the truncated Q function, the truncated long-term reward, and doing the truncated policy gradient, and we're able to develop the method. And by putting them comparison, for the active critique, use the full information. You're going to use the full Q function, global information, do the gradient evaluation. And then for the scalable method, we're just going to use the local Q function and use the local summation, and everything works. The good thing for these approaches, as you can see, for each step, we develop it in a rigorous way. So there's no surprising thing for the final theorem we can guarantee. Like for the audience who is not really interested in the theoretical guarantee, just want to highlight is we have two components in theoretical guarantee. One is just naturally from the learning method with the sample complexity we can achieve, which is consistent with the IO in the literature. And then the other one, which can design as a tuning parameter. So if I have more computation and the memory, then I can put in the K with the K hop of neighbor. I can make the K be larger. And that can reduce my steady state error eventually. And you look at here, this the sample complexity is almost a fixed number. It's not going to grow up with the increase of size of the network. It's only depending how big is your K help neighbor, which we got like scale-free method. And we did a simulation, and this simulation is on the multi-access wireless communication. I won't talk about details, right? What is that network being there? I want to highlight for the graph. So the K means how many neighbors I may look at. So I put in the K equals 0 means I totally ignore everyone else's information, just use my own information to do my learning, which already can outperform an algorithm that's being used in industry. Once I add like one neighbor, just one half neighbor, I can further improve my information. And this still like ongoing work because the sample complexity, look at how long it took me to learn this school policy. It still took me a long time. So this actually motivates us to think about more. Can we actually use some warm start, use some model-based method to make the initial learning phase faster? So in summary, for the first part of work, I kind of showing the challenges for the network system. Like the scalability is always the biggest challenging and the information constraint. What we were doing is we identify what the property for this system, and we use the network structure to develop the truncated Q function, and then we have a scalable reinforcement learning method. So lots of extension we have been working on right now, like extend to some other type of IO problem, and like to also generalize this truncation method to some other IO method to see how general this method is for some other multi-agent IO setting. So with that, I want to, before the second part work, I want to highlight is for the multi-agent IO, sometimes I think the biggest challenge is to find the right problem for the physical system. There are many different ways to model the multi-agent IO, and if you open a paper, people have a different kind of setting. So indeed, we also have some other setting. For example, this is more connected with real-time and continuous state, continuous action space, and I have a dynamical system. And then sometimes it's actually hard to really model the underlying, even the network locality constraint. So we have one way, just like look at here, every agent has some partial observation, and how can I really find the good policy to eventually minimize global cost or maximize global reward. And then some example we can think about is the thermal control for big building. We had some other method, like for this one, we do not need too much assumption and developing some other communication scheme, and still we guarantee the stability guarantee and we guarantee the efficient sample complexity. And there's another thing for some of the audience who is more technical, I want to highlight another one, is about optimality guarantee. So when we're doing the theoretical analysis, we say optimality guarantee in terms of the stationary, that's the gradient norm. And this is actually not really the optimality guarantee. Like the global cost function probably still be far away, even my gradient is small. That's motivate us to really think about what's exactly the point I'm really converge to. So we had a different part of work. One is like really handle the partial observed system, like what exactly the station point is. There's an ongoing collaboration with Professor Fazl's group at U here. So it's a very exciting collaboration. And we also have other like multi-agent MVP to bring the agent self-interest behave into study, which is another challenge. So with that, I would like to move the second part of the talk, but if you have questions, feel free to ask me. Hope it's still like accessible. Yes.
So in the first example,
yes,
you're looking at just the neighbor.
Yes.
And then that's a prediction of the whole system. Yes. But how do you handle neighbors that have varying input, or is that not an assumption?
So for here, we do not need to assume it's homogeneous interaction. So they can be heterogeneous, and which is fine. But during the learning process, we have the QI, everyone's QI is different. So if like some neighbors has higher weight, it will showing effect in the QI evaluation.
And is that, if you have a high impact neighbor that's say one step outside your circle, how does that?
So then that's what probably the decaying factor role, which is not like, for example, will be closer to 1 rather than like relatively small. So we're making the gap become bigger. Yeah. Yeah. Thank you for the question. Good question. Good. So I'm going to move to the second part. How many times? Good it on time. So like the second one, I really want to bring the safety into the discussion. Like the first one, you can imagine like I have an overall asymptotic guarantee, some complexity, but I don't have additional constraint on the state on action, which is usually not the case for the real physical system. And for the second one, we really dive into those physical system where the safety is critical. And like this is just some examples. I think almost all the physical system safety is critical. And the challenge I put in safety, but I want to highlight one thing. If we just worry about safety, right? One lazy choice is don't drive, don't play your drone, right? Don't open my manufacturing. Right. The real difficulty is actually I want to guarantee safety, but still achieve good performance. That is a challenge. There's a trade-off between them. Right? If I become too conservative, don't do anything, I'm not going to achieve anything. So this is a challenge, safety, good performance. How exactly the two objectives affect each other? What's the trade-off between them? That's a question we want to ask. So what's the framework that we can study this problem from a mathematical point of view? So the framework is constrained control. So like some of you are expert in MPC, like this whole formulation probably looks very familiar with you, like Steve, who has a very nice lectures on MPC. So this is a constraint control that people start with talking about safety constraint. So let me go through what exactly this means. So think about the quadrotor. Like we have a dynamical system. That's what tells like my control, once I put in my control, and also disturbances, what's the next state for this system going to be? And we have a constraint, which defines the safety constraint. So and we have a cost function, like when we fly, probably want the quadrotor to follow a certain trajectory with a minimal like energy going to consume. So this is a quite general framework. And there's a multiple uncertainty here. First is the model. Depending on the environment, we actually never really have an accurate model for this because the model parameter will have some drifting depending on the environment. Right? The model either unknown or uncertain or partially known. And there's also disturbances in this system. It's very hard to model what exactly the real disturbance is. I need to design a control mechanism that's work for a broad class of disturbances. So like in general, when we're dealing with the uncertain model, like the loop people have been doing, right? System with uncertain model, take action, policy update, and that will learn the model on the fly. So I'm going to talk about like the kind of single trajectory case. I want to update and learn my model on the fly. How is it possible to still guarantee safety? And as I mentioned, the difficulty is to ensure both the optimality and also the safety. This is the tension between these two objectives. Surprisingly, the problem is surprisingly difficult. Even the mathematical formulation looks so elegant. It's surprisingly difficult even for the linear systems. Like when we dig into the literature, even we have a linear dynamical system, just as the ABC that's governed the dynamics. And we have a linear constraint. Okay, just linear constraint. And people already give me the constraint. Even not talking about getting constraint from the perception. But let's say the constraint even is already given. And I wanted to find a policy to minimize quadratic cost. So if you dig into the control literature, even this problem is still hard. What do I mean by it hard? First, there's no computationally efficient algorithm, even when we have a no model. To solve it quickly, satisfy all the constraints, or under what kind of conditions I can making sure this problem is always safe or feasible. Even those ones still unknown questions, we don't have a computational efficient algorithm. So what people do is that then people are going to relax, like, hey, rather than to think about the optimal policy among all the policy class, let's just like narrow down, think about some special policies, which is easier to analyze. Like first, some policy I'm going to also mention, like think about the linear policy and a fine disturbance feedback policy, a robust MPC, using optimization tool directly to solve it and taking the first action. And some like people change the cost function to the penalty function, like the barrier function. So this is how people are going to handle this problem, even for the linear system. Now, for the unknown, you can imagine will become even challenging. So when people study the unknown system, the criteria people are going to put like something called regret. I want to develop my learning algorithm, and I want to benchmark with some optimal policy. As I said, to find optimal policy is difficult. So then people will say, okay, how about practical optimality goal? What's a practical optimality goal is I only want to benchmark with some optimal policy which people know how to solve. So we can, let's call it the practical optimality goal. Not really solving the optimal policy for the entire problem, which does not exist yet. So let me look at the problem. So the literature, give a quick literature review. As I mentioned, like this problem has been happening in engineering a long time. Definitely, there's lots of solutions people can go ahead to use. But those methods work very well in practice. But if I look at the fundamental, like the hard performance guarantee, what exactly we can really achieve? They still lack those optimality guarantee and also safety guarantee. Like what exact feasibility we can really achieve? And second, then from the learning community, people also started looking into this problem, and then they developing different type of learning schemes. And this is some literature from the learning community. Like I can make the constraint be soft, and I can use in those LQR problem to solve it. I can use like just think about unconstrained to see how well I can really handle the constraint. As that this lacks the safety guarantee on the hard constraints application. And there are some recent work really go ahead to handle the real challenges. And you can look at the year, right? So very recent papers, people studying to tackle this problem. So the question still, like how, as I mentioned, how to really achieve the good balance between the safety and optimality guarantee. So what the solution we do? Let me first come back to the offline solution for the known model. As I mentioned before, for the system itself, even we know all the parameters, it's still hard to solve. So first, then we actually change our goal. There's so many different ways we can specify our control policy. So this control policy called a fine distance policy. What this means is rather than to typically people familiar with the state feedback control based on my state taking a control action. So this policy class is defining the map between the disturbances and the control action directly. And just using the linear mapping between the control action and disturbances. So there are studies about like where this policy comes from, how good this policy is going to approximate state feedback policy. So what's the advantage for doing it? The advantage if still this is my constrained LQR problem, if I just look at my control policy in that class, I can change my problem to be an optimization problem that I can use optimization solver to solve. And what do I mean by I can use optimization solver to solve? I really mean we can use coverage programming to have a hard guarantee about what's the optimality of this optimization problem, rather than just approximate local solution. So why? So now I'm going to dive into details. So the advantage by using that policy is now I can change my problem to be a linearly constrained quadratic programming, and which there's so many solvers we can use. Because of this nice structure, and then how are we going to deal with the unknown model? So the challenge for the unknown model is this. So I don't know my A star, B star, right? The best way I can go ahead to learn it. But when we go ahead to learn it, by combining with the statistical learning approach, what usually we have? We have an estimated value. But since I want to guarantee safety for the real system, I need also take into account of my estimation error bound. So if I have both of them, in order to keep the hard performance guarantee on the safety, what we're going to do is we can make our optimal optimization problem become less aggressive and more conservative by shrink the safe constraint. So the additional thing is like we add a little bit buffering. And if I really want to do a good performance, it's better for me to have a better uncertainty quantification. Then while adding buffering, I'm not losing too much optimality. So this is the overall idea how we're going to deal with for the unknown system to guarantee safety. Put in the overview, what we're going to do is we first do the model estimation. You can use a different method to do the model estimation. And for the model estimation, we need two outcomes. We would like to have the estimated model, but we also want to know the estimation error bound, which is called uncertainty quantification, to allow me to do the robust safe control design. And then I can do the safe exploitation of the model. I can use my model and my uncertain qualification to develop my good control policy and to ensure the system is safe. If I want to continue to learn my model better, as I mentioned, the multiple reasons why we want to continue to learn the model is also has some drifting. Even your original model estimation is very good, but probably it's not going to be good after a while. So this another phase is, in order to learn the model, we should add some exploration, like the random noise, to make my data become more informative. Then I can go back to do my model estimation. Like, you look at the overall architecture is quite straightforward. The challenges is, first, as mentioned, if I want really do a good balance between the safety and optimality, I should have very good uncertainty qualification. This problem is actually difficult, even for linear system. The reason is, like, we are doing with a single trajectory, and we have the feedback control policy kind of changing my state and control action. Like, from the statistical point of view, there's a lot of correlation in the data, and which making those textbook 101 statistical learning is not really able to apply here for this scenario. And second thing is here. So it looks like I have the robust safe for each stage when I develop the policy. There's one issue. Even we have a control policy, which is safe individually, if I start with the same initial state, but once I just do the switch between the safe policy does not really mean the switch actually will becoming safe. I will show you examples. So for the two issues, first thing we actually look into the model estimation, go ahead to think about our own model estimation. Can we have certain meaningful bound? So we are actually able to have an uncertain qualification for the general linear case under some assumptions. And this bound can give us the information that we need to the robust safety control design. If you guys are interested, like the paper is on archive, has like, we use the martingale analysis to get in this uncertain qualification. So now about the second challenges. As I mentioned, I have a two safe policy. Like this is M1 is safe policy, starting with time equals 0, M2 is safe policy. And when we do the simulation, just like at a certain time, change my policy. You can look at here, it becomes unsafe. The reason is because when we design the safe policy, we're just solving those kind of optimization problem, which is different from the optimization problem that's really handle the switch. So how are we going to solve that one? So what we doing is here, every time we really want to change the control policy, the abrupt change is not good. The way we're going to do it is find the robust safe policy set and also the new robust safety policy set. When we design it, we're actually making sure they overlap. So then we can find there's some middle policy, which is safe for both scenarios. Then in the control design, the way we're going to do it is just gradually change my safe policy to the middle policy, and then gradually change to the ultimate policy that we want to go. With both of them, now you can see for the entire algorithm, what we're going to do have a three, for each episode, we have a three phase. And I want to highlight the algorithm is like on the fly. We never really fly back to the initial value because for many physical systems, once you click starting button, the system just continue. So we have model estimation on the fly, then we first do some exploitation. The exploitation is a good way to ensure my optimality guarantee. And then we add the exploration, adding the noise, and go back to do my model estimation. It looks like straightforward, but each step looks complicated. And so for each one, we need to change the policy to the safe transit. So, but we had spent a lot of time trying to figure out the right parameter to choose. We can mathematically even guarantee, no matter what happens, as long as the original problem is feasible, our method is always going to be feasible, and we can guarantee safety all the time. And another interesting question about optimality guarantee. So optimality guarantee, what do we compare is our own control algorithm, the online control algorithm, with the optimal policy for the no model. And what we are able to show the regret is t to the power 2/3. So some of you probably familiar with those kind of regret bounds. Sometimes I want to highlight this. When we look into the literature, when people ignore the safety, what people can achieve is square root of t. So the lower the regret, the better. And there's another literature was trying to add a robustness in like robust stability. And then that regret bound, it looks very similar to our regret bound. So there's one fundamental question we want to ask is like, definitely now you can see there is a trade-off between the robustness, safety, and optimality. For the optimality, we got this kind of T to the 2/3. One question is this really fundamental? That's weak for the achievability, which is the ongoing work. Hopefully we will have some answer in the near future. So this is some numerical test, a simple test we did for the quadrotor vertex flight, just like one dimension. And we put in the goal like this, like ceiling, and we wouldn't want the quadrotor to just crush the ceiling. And you can look at here without doing the safe adaptive control. Initially, you just like go ahead because I have lots of exploration to my learning system. It's about hitting the ceiling. But with our algorithm, you can gradually, it's become more conservative, but gradually it's going to learn the true model and still ensure the safety all the time. So with that, I want to conclude the second part of work. As you can see, we took the very intuitive framework, but then just go ahead to working on each part. What are the challenges? Can we make it better? Can we really study the trade-off? And then a lot of like future work. Like first one is conservativeness. Is our method really conservative? Actually, it's already kind of optimal performance guarantee. And we're actually more interested in like to study the robust MPC approach because at least empirically, people already show those robust MPC work well in reality. How about to study the hard performance guarantee for the robust MPC rather than the policy I was showing here? And there are many other cases that I've been working on, especially for the time varying disturbances, like all those cases, because the system is not really that stochastic, you have a little more information of what the disturbance is going to look like. So with that, I would like to conclude my talk. As you can see, I kind of put in the two examples, talk about the scalability and then talk about safety. And for each one, if now you think about first part, it's more like the model-free approach, just taking the control policy, look at the outcome, and taking the update. For the second one, we did a lot of model-based method. A general question, which I don't have answer, but I think that's will happen in the future, is when we really want a very powerful learning method for physical system, like we should better integrate the advantage from both sides. But how to integrate them, which is a more challenging question, probably depending on the application. With that, I would like to conclude my talk since my computer even don't want me to go to the next slide. Only one slide left. Thank you so much.
Thank you for the great talk.
Thank you.
So time for questions from the audience. Yeah.
Great question. So back to the first part of the presentation. For whom to communicate, how would you define reward?
How do I define what?
How would you define your reward? And what is the behavior and goals of your agent changing time?
That's a good question. So for the first part work, as I said, like for the problem setup, it's a stationary environment, right? The transition probability, like we didn't really study the time varying case. And for the time varying case, I can still go ahead using my method, but then the analysis, rather than to say I convert to optimal policy, because there's no such optimal policy, right? The optimal policy is changing. So the analysis will be coming, understand like the regret analysis or like a competitive ratio. So we have one paper, not really doing the network case, but like just a general time varying MDP. How good, like how should I define my Q function? Like should I add in some inertia when I evaluate? Because like depending how fast the system is changing, I probably should even forget the history and pay more attention on the recent history. Yeah, so kind of like it's not studying this work, but that's an important question.
Would that be possible to apply techniques to provide learning into the real world?
Yes, depending on what kind of unsupervised learning you're talking about. Yeah. Yes. Yeah, hot.
So how do you, when implementing uncertainty, how do you differentiate between sort of uncertainty that's because the model is incorrect or it doesn't have enough data versus uncertainty that's inherent to the physics of quantum? So this is inherent to the process.
Okay, that's a great question. So for this part, the uncertainty quantification we have yet is about the linear system structure. So the one underlying assumption is a true model sitting in the linear class. One generalization we have been doing is to doing the linear, like the in the kernel space, right? You can handle the non-linear, but the kind of in the kernel space. So that's kind of one assumption. It's really neat kind of says sitting in that the class of the models. And we had a recent work, which is actually a negative message is this. So if the system originally, right, it's actually not really sitting in the model of the class. And we really go ahead to handle the approximation error, because for example, if I really go ahead with the kernel, I using, like if I have the more basis function, it can definitely approximate the whatever true underlying physical system, but I often need to truncate, like how many basis function I need to use. So we had a recent study showing that approximation error, like even it can be small for the learning phase, but once we go ahead using that one to design the control, it can propagate. We haven't figured out a solution to handle that yet, which is I think is very, very important question for the nonlinear control. Yeah. Thank you.
Thank you very much.
So I also have a question about the first work. So you said there is a K-pop algorithm that basically selects the K neighbors. And so have you considered cases where you increase the K a lot? And also, does your algorithm handle, let's say, automatically select the K relevance? Because even though there are like K neighbors around it, but there are maybe some agents are more important to take care of when you make the next move.
Yeah, that's also a very good question. So we did some like simple network. We're actually making the K from 0 to the diameter of the network, actually, which is a line case. And we can show like the benefit for having more K. Indeed, kind of exponential decaying as predicted in the theorem itself. And I think that's kind of partial answer to your question. Another thing is this. So I think one of your questions is asking, even my model can handle heterogeneous connection, but I kind of only kind of just K-hop neighbor. If I'm doing the one-hop neighbor, then including all the one-hop neighbor. But then even for the one-hop neighbor, some neighbor probably not really play an important role. And so far, our study haven't really addressed that yet. Yeah. But empirically, you can just go ahead, like ignore the agent information to see how it look like. But we haven't really done that. Yeah. Thank you.
Looks like we have another question coming up.
Yes. Thank you.
Very nice talk. I was just wondering about part one. How applicable do you think that would be to really high-dimensional partial differential equation systems, whether simulation and just really any?
I mean, partially, okay. This is a great topic because I have a lot of things to say about that. So for the PDE, two directions we have been doing. First of all, for the network model, right? So for the model I put in here, it's kind of discrete, and discrete states, discrete action. And the PDE system itself, naturally given those kind of network. One of my students actually looking into that, but we again make it like called a spatially distributed system. Like for certain kind of PDE, probably the method I'm presenting will still hold. So that's one. And second is I'm talking with another professor in our mathematics who is doing PDE. He's actually using the multi-agent RL to build the PDE simulator for PDE. So what he did, like you put in like discretize. I'm just saying, according to my own understanding, probably we should not read the case. So you discretize the like space of the entire the PDE the space, and then you put in a lot of those grades. And then for each grade, you can treat it as a multi-agent, and then you go back to using those reinforcement learning, like assuming there's an underlying objective function, and to using some neighboring grade information to help you to simulate the trajectory. Yeah, this is just like a new topic we started talking with each other. Hope does that answer your question? Kind of, yeah. So I think there's a lot of room for the multi-agent RL connection with the PDE, like on different directions. Yeah. Thank you.
Yes, thank you so much for the amazing talk. I have a question about the part one.
Yes.
What happens if one of the nodes just go offline? So you have a network, and in real scenario, maybe you have extreme values, right? And maybe some of the nodes just go offline, and how robust is that case?
Yeah. Okay, great. So for those situations, I think the method is able to handle. And for example, right, if one network, put it this way, so if the network is becoming like different network, some node getting changed, and automatically for my learning method, when I learn those local Q function, so automatically some agent information is getting removed. So if for a certain time period, right, the network is not changing, I can learn the good control policy for the new network. But a more challenging question, if the network just like keep time varying, I can still go ahead to apply my master, but what exactly guaranteed by my master, which I don't have an answer right now. Yeah, thank you. Great, thank you for all the amazing questions.
Yeah, any other questions from the audience? Well, if not, let's thank Lena again. Thank you.
Great, thank you. Thank you, everyone.
We're out of time now for lunch. We have a nice, healthy 2-hour block. So please meet up with people, try to meet new people. We have box lunches upstairs in the ballroom. So if you walk out, upstairs,